Hello everyone, my name is Sarabi Isa. Welcome to our new tutorial video on the continuation of solving problems of thermodynamics of MIT. This is problem 12 from our problem set. So we start with reading the question as usual. A rigid tank initially contains 3 kilograms of air at 500 kilofa and 290 Kelvin. The tank is connected by the valve to a piston cylinder assembling oriented vertically and contain 0.05 meter cube of air. The gas constant of air is 287 joule per kilogram per Kelvin, and specific capacity of air is 716 joule per kilogram per Kelvin at 200 kilofa and 290 Kelvin. The cylinder and tank are in contact with a thermal reservoir at 290 Kelvin. Also, the valve is closed. A slow leak allows air to flow into the cylinder until the tank pressure fell to 200 kilofa. The weight of the piston and the pressure of the atmosphere maintain a constant pressure of 200 kilofa in a cylinder. Assume the volume of 5 connecting the tank and piston cylinder is negligible. What is the total work transfer and heat transfer for the air? Find the entropy change of the heat reservoir. Determine the entropy generated in air during this process. So that is the question. So we start with a solution as usual. Solution. So we have given a system. So assuming this is a cylinder which is a thermal reservoir at 290 kilofa. So let me name this system as system C. So and I have air here. Inside this I have the volume of air which is 0.05 meter cube, and I have a pressure which is 200 kilofa. So I name this to be system A. So also I have the mass here of air which is 3 kilogram, and I have a pressure which is 500 kilofa. So I name this system to be system B. This has a temperature of 290, and also this has a temperature of 290 K. So to avoid confusion, I will let every parameter or properties of the system to subscribe its system. For example, I let PA, that's the volume of A, to be equal to the given volume which is 0.05 meter cube. So also I have PA, that's the pressure which is 200 kilofa, and I have also TA which is 290 Kelvin, and PB is equal to 500 kilofa. Okay, and also MB, the mass, which is 3 kilogram. So TB is equal to TA, which is 290 Kelvin. So that is the parameter given to get the volume after leakaging, that is BB. We apply the equation of state, that is PBBB is MBRTB. So BB is equal to MBRTB all over PB. So I will substitute the given values, which is 3 times the temperature all over the pressure, which is 500 kilofa. I convert it to normal Pascal, which I multiply by 10 to the power of 3. So BB is equal to 0.4993H, approximately 0.5 meter cube. So now in A, we ask to find the work done or the work transfer. So we consider the work done during constant temperature with changing pressure. So we see the temperature is constant, T is constant, but pressure is varying. So what is the formula for finding work done during? So therefore, so that is the formula. So work done will be equal to minus 0.5 into 200 minus 500. So this work done will be equal to minus 0.5 times minus 300. So work done is equal to 150 kilojoule, since pressure is in kilofa. So that is the work done. So that is the work transfer. So to get the heat transfer, we apply the first law of thermodynamics. So the first law of thermodynamics. Now temperature is constant, so Q minus W is equal to dE. That is the change in energy. So if temperature is constant, what will this be? Is the same as dE A plus dE B. So temperature is constant in A, also temperature is constant. So therefore the heat transfer is equal to the work transfer. So heat transfer is equal to the work transfer, which is 150 kilojoule. So that is the heat transfer. Then B, we ask to find the entropy transfer. So the entropy transfer in the thermal reservoir. So ds is equal to the S transfer plus the entropy generated. So in thermal reservoir, reversible process occur, no entropy that will be generated. So ds is equal to the integral of dq all over the constant temperature. So ds is equal to the heat transfer to from the thermal reservoir, that is the heat is lost, so it's going to be negative because heat is lost from the heat reservoir or thermal reservoir to the air, so it's negative here. So we have minus q 1 to 2 over the temperature, which is minus 150 kilojoule. I multiply it by 10 to the power of 3 to convert it to joule all over the constant temperature, which is 290. So by computation I get minus 517.24 kilojoule per Kelvin. So that is the entropy transfer. So now see, we asked to find the entropy generated in that process to apply the second law of thermodynamics. So now in the tanks, what will be the entropy transfer? So the entropy transfer in the tank will be equal to the integral of Q all over the temperature. So now the Q here is positive because heat is gained by the two tanks. So heat is gained by the two tanks, so which is equal to all over 290. So now the S transfer is equal to 517.24 joule per kilogram. So now since I'm talking about the two tanks, then the change in entropy, that the total entropy will be equal to the change in entropy in A plus the change in entropy in B. So note TA is constant, that is TA1 is equal to TA2, which is equal to 290 Kelvin. Also, pressure is constant, as we read in the question. They say during the pressure is maintained. So the pressure in A also is constant. So the pressure in A is constant. Which is 200 kilo far. Therefore, the entropy of A separately will be equal to the M A and CB plus R ln TA2 over TA1, then minus MAR ln PA2 over PA1. So now the temperature is constant, so the logarithm is 0. Also here is 0. So therefore entropy in A is 0. So the reversible process occur in A. So now in B, temperature is also constant. So TB1 is equal to TB2, which is 290 Kelvin. So what is PB1? So PB1 is equal to is equal to 500 kilofarad. So PV2 is equal to PA2, which is 200 kilofarad. So the pressure 2 in B is equal to pressure 2 in A. They should have the same pressure from the statement given. So therefore, the entropy in B is what? MB into CB plus R ln TB1 2 over 1 minus MB R ln PB 2 over PB1. So the temperature is constant. This is 0. So the entropy of B is equal to minus MB R ln PB2 over PB1. So the entropy is equal to minus 3 times the gas constant, which is 2H7 ln 200 over 500. So what is 8? So the entropy in B is equal to 7HH 0.93 joule per Kelvin. Therefore, the total entropy is equal to dSA plus dSB, which is equal to 0 plus 7HH.93. So the change in entropy total will be equal to 7HH.93 joule per Kelvin. So what is S gen? So the S is equal to the S transfer plus the S generated. So the S gen is equal to the entropy change minus the S transfer. So the S generated is equal to, what is the S? 7HH.93 minus the S gen, which is 517.24. So by subtraction, the entropy generated is equal to 271.6H6 joule per Kelvin, which is greater than 0. The process is irreversible. So that is. Thank you very much for watching. I remember my humble self, Inusarabi Isa, popularly known as Bodemas. Bear with us in our next video. Thank you very much for watching.